All right, let's take a look at the Unit 7 Solutions All About Molarity lesson together. So you probably have heard about solutions before, but maybe you haven't thought about exactly what it means to be a solution. Water, like pure water, is not a solution, but tap water is, because the definition of a solution is when you've got a solute dissolved in it. So, for example, the ocean is a solution because it's salt dissolved in water. And solutions can have different concentrations, and that's important to know. So, for example, if is a lot of solute dissolved in a solvent like water, the concentration is going to be high because that means there are many moles for every 1 liter of solution. On the other hand, something that has a weak concentration means it has less moles per liter. And then there are also some terms that you've probably heard of, homogeneous and heterogeneous. It just basically means, is the mixture uniform or is it chunky? And there are some examples there as well. Okay, so let's talk through the introduction. One of these beakers has a very dilute, it's basically water, solution in it of sulfuric acid, and the other one is very, very concentrated. Can you tell which is which? No. So we're going to talk about how you can figure that out in a few different ways in our upcoming lessons. But let's figure out, what it would look like at the molecular level. So some of these terms we've already talked through. Let's go over molarity again. It's the number of moles of solute dissolved in 1 liter of solution. Remember, a mole of anything is 6.02 times 10 to the 23rd. So if you have 1 molar salt water, that means there are this many moles of NaCl dissolved in just 1 liter of water. Okay, so remember, a gallon of something is like 2.67 liters. So, that will help you kind of visualize a liter, about a third of a gallon of milk. So back to my original question, it says the beaker on the left actually had a really high molarity and the beaker on the right had a low molarity. Okay, well, what would that mean? Well, if it's got a really high molarity, like 18 molar, that means there are 18 times 6.02 times 10 to the 23rd molecules dissolved in that 1 liter. And the other beaker, let's say, just had 0.1 moles of molecules. So that's a lot fewer dissolved in 1 liter of water to make that solution. Okay, so what if we were trying to draw those 2 solutions? So we've got a 1 molar solution of sulfuric acid, and then let's draw relative to that. What would it need to be 18 molar? So this one, let's kind of do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and then let's say we wanted to make this accurate, which I don't recommend, but if it's 18 times more concentrated, 0.1 to 18, 180 times more concentrated, 180 times 12, I would need to draw 2,160 dots here to show that it's 180 times more concentrated. No, I'm not going to be doing that, but you kind of get the point. It's got a much higher molarity. Okay, there we go. All right, so let's do something. So this was your assignment to get ready for this by having some cups, measuring cups, some teaspoons, sugar, something that you can dilute, and cups to put the solutions in. So there's 2 ways that scientists make a solution. They add a solute to a solvent and it dissolves, or they have a stock solution, a concentrated acid, for example. They measure part of it out and add water to make a new solution with a lower concentration. Okay, so we're about to do both of those. Okay, so Let's say you've got a measuring cup, add 1 teaspoon of sugar to it and fill to the 1/4 cup line with water. Stir it, move it into a cup. Do this again, only do 2 teaspoons of sugar in your second cup, and then do 3 teaspoons of sugar in your third cup. Okay, and then you're going to stir all of those and you're going to taste them. And we'll be drawing a little sketch. So let's do that now. Then we'll come up and look at the directions for way number 2. So cup number 1, we had 1 teaspoon of sugar added. Cup number 2, we had 2. Cup number 3, 3. Hopefully your taste buds were working and you should have gotten sweet, sweeter, and obviously the one with the most sugar in it, cup number 3, is going to be the sweetest. That's the most concentrated. So if we're going to sketch these at the molecular level, okay, we've got one with 3 dots. This one is twice as concentrated, so I'm going to just draw 6 dots. You could draw different numbers too. This is a very generic representation, but basically more dots in the same amount of area. You can sort of think of it like density too. It's more dense, it's more concentrated. Okay, now let's talk about the second way that scientists make a solution. Let's say you've got some Gatorade at home. Okay, add 1/4 of a cup of the Gatorade to cup number 4. Add 1/4 cup of water, stir it, taste your original beverage, and taste the new diluted one and compare. Okay, so your original beverage should have tasted good. Okay, and your cup number 4, where it's now 50% water, should have tasted watered down, weak, probably gross. Okay, so at the molecular level, we have this original beverage, and now we've got twice as much water, so it's half as concentrated. So the particles now have more space to move around. Okay, so let's talk about calculating molarity. So to calculate the concentration, you take moles divided by liters. So for example, if you've got 5 moles of salt in 10 liters of ocean water, 5 divided by 10 is 0.5 molar. Okay, so let's do a couple practice problems. Let's do 2 moles divided by 4 liters. What would the concentration of this glucose solution be? 0.5 molar glucose. Now, sometimes problems are annoying and they make you first convert from milliliters to liters. Okay, so let's do the molarity of this KBr solution. So again, we've got moles divided by liters, so 0.80 moles divided by 0.4 liters. And our answer would be 2 molar KBr. So it's as easy as that to calculate molarity. Okay, so let's talk about the teaspoon of sucrose that we added to the 1/4 cup of water. So a teaspoon is 4.2 grams. So if we want to know moles per liter, we've got to first get grams into moles. So in order to do that, you need your trusted old friend, the periodic table, to add up 12 carbons plus 22 hydrogens plus 11 oxygens. So you add all that up and that comes out to be 342.3. So now you're going to do 4.2 grams. You don't even have a whole mole because a mole weighs a lot more. So you have a fraction of a mole. You've got 0.012 moles of sucrose. So then we do what we were doing in the other problems. Take moles divided by liters. A 1/4 cup, which is what we used in our experiment, is 0.06 liters. So you'll take 0.012 divided by 0.06, and you get your concentration. So let's do another problem. So this time it's 8.4 grams of sucrose. And we want to know the concentration. So once again, we've got to divide by 342.3 grams for every 1 mole of C12H22O11. And I'm going to punch that into my calculator. That is 0.025 moles of sucrose. Then we take moles divided by liters and punch that into our calculator. It came out to be, just as we predicted, about double the answer to number 2 up here, because we had twice as much, or I should say twice as much as the example, not number 2. So our concentration was about double. These are rounded slightly differently. All right, next we've got 12.6 grams of sucrose. And we want to figure out what was the concentration when we added 3 teaspoons. So once again, divide by 342.3 grams. And punch this into your calculator. I get 0.11 moles. Oops, sorry, looking at the wrong thing. I get 0.037 moles of sucrose. Divide by liters, which is again 0.06. That's the quarter cup that we had the total volume at. And the final answer is 0.62 molar sucrose. Which makes sense because the third cup was the most concentrated. All right, let's talk about a can of Coke. A can of Coke has 37 grams of sucrose. So we need to get that into moles because we're going to be finding the concentration of sugar in a can of Coke. There we go. So 37 divided by 342.3, that's 0.11 moles. And it says the volume of a 12-ounce can of Coke is 0.35 liters. So the concentration is 0.31 molar. So which cup was closest to the molarity of the sucrose in a can of Coke? So it would be between cup number 1 and 2, about halfway between. So between cup number 1 and number 2. Fun fact, chemists don't actually use measuring cups in the lab. They use volumetric flasks to make accurate concentrations of solutions. All right, now we're going to do a different method of figuring out how to make an exact concentration of a solution. This time, rather than adding a solute like sugar to a liquid, we're going to take something that already has sugar in it, let's say a Gatorade, not a sugar-free, but a regular Gatorade, and we're going to just pretend it has a concentration of 2.0 molar. Okay, just we're being generic here. Let's pretend that you want to make a half of a liter of a 1 molar solution from this 2 molar solution. How are you going to do this? Well, there's a handy dandy equation. M1 times V1 equals M2 times V2. M1 is the molarity of your stock solution. So your highly concentrated solution that you're going to make a weaker solution from. V1 is the volume of the concentrated solution that you should start to make your solution. So basically, this is the one that's the mystery that you're going to solve for in our problem. M2 is the molarity of our dilute solution, what we're trying to make. And V2 is the volume of our dilute solution, how much we're trying to make. So once we plug in the numbers, so M1 was 2, V1 we don't know, M2 was 1, and V2 was 0.5, we need to do some algebra to isolate V1. So we divide both sides by 2 molar, and we get a V1 of 0.25 liters. Well, what does that really mean? That means that if we want to make this weaker solution, we need to take 0.25 liters of the original beverage and add water until the total volume is 0.5 liters, and then we'll have our 1 molar solution. So in other words, we would need to have our volumetric flask. Oops, that looks like an Erlenmeyer flask. Let me try again. Okay, volumetric flasks are the ones with the long neck. Okay, and let's say this is the 0.5 liter line. You would fill it halfway with your stock solution. So this is the 2.0 molar solution. And you would fill it the rest of the way with water. So this is just water. And then you would mix it up. And then once it's mixed up, oops, that didn't change, that's okay. It's going to be a mixture of the water and the solution. So now the entire thing has a weaker concentration because half of it's water. So which picture is more accurate to tell us about what's going on here? This one has 8 dots, and then it looks like the volume goes up, but there's still 8 dots. This one has 8 dots, and the volume went up, but now it has 16 dots. Hopefully you're thinking A in your head, because really we're not changing the amount of solute that's in there. We're just weakening the concentration when we add water. So it's still 8 dots. It's just going to be spread out more. Okay, and let's do our last question here. It says we've got to make 1 liter of a 3 molar solution. We've got a 12 molar stock solution to work with. Okay, so we know that this is our most concentrated solution, and we don't know V1. But we do know we want to make a 3 molar solution, and we want to make 1 liter of it. So we're going to divide both sides by 12. And V1 is going to come out to be 0.025 liters. And it's like the same as the example, only it's going to be different. Okay, so this time we've got a 1 liter container, and we want to put 1/4 of it with our stock solution. So this is our 3 molar solution. And then we're going to fill to the line with water. So it's really going to be 0.075 liters of water, right? Because this was, 0.25 liters. Okay, then we're going to mix it up. Okay, so that the water is mixed with the solute, and now the entire concentration is weaker than the 3 molar. It's only, oh, oops, I did this wrong. Sorry. I'm not re-recording this whole video. This was 12 molar, the stock solution, and now once it's mixed, now it's the weaker 3 molar. Sorry if that was messing with you. A lot of numbers. So these are the basics of again, how scientists make concentrations. And so it's really important to know the basics when it comes to molarity. So hope you guys are doing well, and thanks for watching this video. Bye.